Welcome back, everyone. For this series of lectures, we're going to cover a lot of the same topics we did before with recurrent neural networks, except now we're going to approach this on a more realistic time series data set. And we'll have to see that we need to do things like help manage and load the data set better using some pandas tools, and we'll also have to prepare the data by normalizing it. All right, let's get started. All right, you can see I've already done some standard imports such as torch, numpy, pandas, and matplotlib. And I've also imported a specialized register matplotlib converters. This has to do with some plotting of date-time values that we'll do later on with matplotlib. So I went ahead and imported that from pandas.plotting. And you can go ahead and run this function, and we'll see what happens later on. But basically, it allows us to make a little bit of a nicer plot with matplotlib due to the fact that this data will be timestamped. Let's go ahead and begin by loading up the data. We already have this data for you in the data folder. So we'll say df dot or is equal to pd.readcsv. And then depending on where you're located, you may need to give the full file path, but underneath the data folder, underneath time series data, there is a file called alcoholsales.csv, which essentially shows beer, wine, and alcohol sales data throughout the couple of previous years. Go ahead and also add in index call is equal to 0, which says grab the first column and set that as your index. And then also say parse underscore dates is equal to true, which will allow pandas to automatically convert the index and to a datetime object. So if we check out the head of this data frame, we can see here that basically it has some sort of kind of random title here for this first column. And this comes from where the actual data is from. It's from the FRED, which is the Federal Reserve Economic Database. And it has sales data of beer, wine, and distilled alcoholic beverages in millions of dollars from January 1992. And if we take a look at the tail end of this, all the way to January 2019. And we actually linked the data source for you in case you want to check it out in the lecture notebook. So keep in mind, sometimes students get confused and they think there's actually two columns here, but it's really just that the index is called date and we have a single column. And we can confirm that by saying df.columns, and we see here we just get back this single. All right, so next what we're going to do is we'll go ahead and check the length of our data set. So check the length of the data frame. We see we have 325. Let's go ahead and say df is equal to df.drop NA and remove any null values in case we have them. If we check the length of our data frame after dropping null values, we realize it's the same length, so it means it did not have null values. If you have null values in your data, you'll have to decide what's the best approach in order to remove them. You can either just drop them using drop NA, or you can fill them in with maybe a mean value in between the dates. It's really up to you. There is no right or wrong approach there, but you will have to do something with those null points. Okay, so we have our data set ready to go. Let's go ahead and plot it out. So I'm going to say df.plot, run this, and I'm going to set the figure size here just a little larger. We'll say figure size or fig size equal to 12 by 4, and we can see this pattern of behavior. So essentially, there appears to be a general increasing trend in sales as the years go by, but there also tends to be some seasonality, and this can be due to things like summer and the different seasons like spring, winter, and then you also have things like January 1st, there's a lot of alcohol sales because of the new year, as well as the holidays like Christmas, etc. So keep that in mind that there's some clear seasonality component as well as a general upward trend. So what we need to do is we need to prepare the data. So if you took a look at this df columns, notice that right now the default data type is actually object. So if we take a look back at df head, it technically is treating these numbers as strings. And what we need them to be are floats. So what we'll do here is we're going to extract values from the CSV file. So I'm going to say y is equal to df, and then essentially copy this kind of strange column name that the Federal Reserve gave it, or the FRED gave it, Federal Reserve for Economic Data. And then we'll say df, and let's grab those values. And we're going to grab them as type, and we'll say float. So now y is essentially this numpy array of all those objects, but now they're floating point numbers. That's shown here by the decimal. Let's go ahead and define a test size. We'll define a test size as a year. So since this is monthly data, we'll go ahead and set 12 points as our test size. So we grab a whole year there. So we'll say test size is equal to 12. So we'll use that last year to kind of compare our predictions. And then let's make a training set. So we'll say the training set is y, starting from all the way to the beginning, minus the test size, so minus that last year. And then we'll say that the test set is equal to y, starting at minus the test size, and then go all the way to the end. So if we take a look at our test set, those actual values, those are the essentially last year's values that we're going to be comparing to. Now it's worth noting that in our previous exercise, the train and test sets were tensors. Here they're NumPy arrays, and this is because of one of the steps we're about to perform outputs an array. So because of that, we'll later on need to transform these into tensors, but not quite yet because we need to normalize the data. So what we want to do is recall that back in the convolutional neural network section, we transformed image files using Torch Vision's normalize method that came built in with transform. So often, recurrent neural networks will perform better due to the way that weights and biases are updates if the dataset is normalized, especially as we can see here that there almost appears to be an order of magnitude change from the very beginning of the dataset, ranging in the thousands, to towards later in the dataset, where you're kind of above the 10,000 range. So especially if you have a very stark increase trend here, you're going to want to normalize these data points. It's always a good call, and it's essentially free to do. So let's go ahead and show you how to do this quickly and easily with scikit-learn. We'll say from sklearn.preprocessing import, and we're going to import min-max scalar. Go ahead and run that. And then we'll create or instantiate a scalar object. So we say scalar, min-max scalar, and what we're going to do is we can specify what range of values we want. So we're going to say the feature range, essentially normalize everything to be from -1 to 1. So all the ratio of the data will be the same. It's just scaled down to only be between -1 and 1. Now, in order to actually perform this calculation, we need to provide the min and max values of our data set. And if you take a look at the lecture notebook that corresponds with this lecture, you can see here that we've actually provided the formula that we're using here. So notice the formula is dependent on your minimum value for x and your maximum value for x. So what we're going to do here is we're actually only going to give the minimum and maximum values based off our training set, because we don't want to perform what's known as data leakage. And data leakage, you can check out an article that we linked to it here in the lecture notebook, but basically it's leaking information from your test set into your processing for your training data. So what we don't want to do is kind of peek into our test set and grab the min and max values from there. Because notice, if we were to just get all our data and grab the x min and x max values, that would be all the way up to here. So what we need to do is make sure we don't leak future information about what our possible max value or minimum values could be. So we're only going to scale this based off the min and max values from the training set. Now that does mean that possibly upon scaling the test set, that the values squeak by a little more than -1 or 1. But that's okay, because what we really don't want to do is assume information about the future test set. So let's go ahead and grab those values. And essentially, these scalars have two steps. There's the fitting step, which is just grabbing the minimum max values. And then there's actually the transformation steps, which is then going to perform the transformation or normalization. So let's go ahead and first fit our scalar. So we'll say scalar fit, and we're going to fit it only to the training set. And in order for this to work, we need to reshape it to -1 by 1. And notice here, I actually didn't assign this scalar to anything. This is essentially an in-place command that informs the min-max scalar what values it should be using in its formula to perform the actual scaling. If I actually want to transform a set, what I need to do is say training normalized is going to be equal to scalar, and then call dot transform, and then pass in this case, my training set, reshaped to -1 by 1. And now if I take a look at my normalized training, notice now all the values are pretty much scaled between -1 and 1. Something to note here is that technically you can do the fitting and transformation in one single step by saying fit underscore transform. But I like teaching it in 2 steps, that way we can understand what each step is doing. Okay, so we have our normalized training set. Now let's go ahead and prepare the data for the long short-term memory units, which recall we need that list of tuples with the sequence and then the label. Recall that the LSTM consumes a window of samples towards that first prediction. So the size of our training set is going to end up being the total size. So recall here, if we take a look at the length of y, it's 325. So we're going to have 325 minus the test size, which then produces 313, minus the window size that we choose. So in this case, I haven't chosen a window size yet, but the window size that we're going to choose is 12 in order to include a full season. So this is essentially our formulation for the size of our training set. Okay, so first we need to convert that train norm from an array to a tensor. So we'll say train norm is going to be now torch dot and call float tensor, and then pass train norm. And we need to view this. We'll say view it as -1. Go ahead and run that. And now if I take a look at train norm, it's essentially the same thing, except now it's this tensor object. And it's not also in the shape of -1 by 1. It's essentially kind of just flat here. So we have our normalized training set now as a PyTorch tensor. Go ahead and define a window size. You can play around with this, but as we mentioned previously in the lecture, especially the theory ones, a good window size is something that takes up at least a whole season. So we can see here there's seasonality, and if you were to zoom in and take a closer look on this data, you can see that one of these cycles is essentially 1 year worth of information. So you should, at the minimum, make your window, especially for your test set, be 12 data points, because this is monthly data, so I have 12 points. If you had daily data, then you'd choose 365 points. Okay, so there's our window size. It's 12. And now we're going to use essentially the same input function we did last time. So let's go ahead and repeat that process, where we have def input data, and we take in a sequence and a window size. And this function is going to create those sequence label tuples. So we start off by creating an empty list called out, and then say capital L is equal to the length of that input sequence. And then let me zoom in here so we can take a look at what's going on here. So we have that input data, and then what we're going to do is say for I in range, that total length minus the window size, essentially what we did last time. Go ahead and define the window as the sequence starting at I, and then go all the way to I plus WS. And this is essentially the exact same function we did last time, which means your label is the point right after this. So starting at I plus that window size, go ahead and grab I plus that window size plus 1. And as I mentioned, you could technically make the label even longer. You could, given maybe 5 points, predict 2 points, or given here the window size of 12 points, predict 12 points into the future. But I would highly recommend that you usually just do 1 point into the future and then see how that performance works, especially after training more and more time. That's usually much more stable than trying to predict a longer term label. Okay, so then what we're going to say is out append, and we're going to append this as a tuple. So notice my double parentheses there. We have the window and the actual label. And then at the end of this for loop, we return out. So now that we have that function, let's go ahead and apply it. So say our final training data is equal to input data, and I pass in train norm, I pass in that window size, and if you check the length of our training data now, it's 301. And does that make sense? Well, if I say 325 minus my actual test size, which was 12, minus my window size, which is also 12, that's 301. So that size does make sense. And let's take a look at what that very first instance of the training data looks like. And just as before, we have this first tensor here, which is the sequence, and then the very next value, which is the label of -1. All right, coming up in part 2, we'll go ahead and define our model, instantiate the model, define loss and optimization functions, and then also train the model. And pretty much that will all be code that we've seen before. All right, I'll see you at the next lecture.